I'm Zu-Ming Jiang from ETH Zurich. I will introduce how to find database bug in this presentation and hope you can enjoy it. So we know there's a lot of various kinds of application, and nearly all of them incorporate database management system. They use database system to store data and manage data. The typical way to interact with database system is using structured query language, etc. SQL. There are very famous database systems like MySQL, PostgreSQL, and SQLite, and so on. Take SQLite as an example. It is used in every mobile phone, Mac, and web browser. So database systems are so widely used in the world, their reliability must be very, very important because any issue there can cause critical impact of its downstream application. But the question is, are they really reliable? We investigate the bug issue fixing commit in SQLite, PostgreSQL, and ClickHouse, and found out mature database systems like PostgreSQL and SQLite suffer from hundreds of issues every year. And emerging database systems like ClickHouse become more and more error-prone when it grows up. We further investigate the commits in 2023 and found out that issue fixing commit occupy about 30% of the all commit. So go back to this question. Are database systems really reliable? Our answer is not yet. So can we propose some way to make database system more reliable? And our research goal is to do that. And our answer to this question is automated testing. Automated testing for database system is not trivial. To test database system, we need to automatically generate test case, etc. SQL query. And when we get the result from the database system, we also need to automatically validate the query result. So there are two main challenges in this domain. First, how to generate effective query to cover database code. Second, how to generate validate query result. We have solved this problem using two new techniques, and today we will discuss the technique related to generally validate the query result. Before discussing the technique details, we need to know why we have to validate the query result. So given a query, if it triggers a crash, there's no doubt that it triggers a bug because database system should not crash when processing a query. But what if it does not crash the system, but the system produces a result? Can we know if the query triggers a bug? To figure it out, we need to validate the correctness of the query. If the result is incorrect, then we can know the query we generate triggers a bug. The question is how to know the query is incorrect. We need test oracle. So the question again, how to construct the test oracle? The key challenge behind the problem is diversity of SQL dialect. We know there's a lot of database systems. They support different features. For example, SQLite support dynamic typing, but Postgres does not. So one database system could produce 0 for this select, but another one could just post an error. So even more, for the same feature, database system could have different implementation. For example, for this query, one of the database, MySQL could produce 1, and another database, SQLite, could produce 0 because MySQL is case insensitive, but SQLite is case sensitive. So the conclusion is, we find it's nearly infeasible to predict the correct result for various SQL dialects because there are different semantics implementation. The second key challenge is the complexity of query semantics. Consider this query. We focus on this select. This select contains a subquery, and the subquery contains a join operation, and also contain an ordering operation. So we found its semantic is very complex. It's very difficult to understand the whole semantic of the whole query. So there are two key challenges. How to solve this challenge? Let's do it one by one. So for the first challenge, we know it's infeasible to predict the correct result, but we may ask, why we predict? Can we use a smarter way? Our answer is yes, we can use a smarter way, and the smarter way is comparison. So given a query and its execution result, we can transform this query into another query in a semantic preserving manner. And we know these two queries are semantically equivalent. Then we send the query again to the database system and get another result. Then we check whether they are the same. They should be the same. For example, we can transform the select 2 plus 1 to select 1 plus 2, and their result should be the same. And we even don't need to know what's the correct result. If the results are not the same, we identified there's a bug. For example, if one select produce 4 and another select produce 3, we know there's a bug. Except the transformation, the whole framework is independent of SQL dialect. So we know if the transformation itself is independent of SQL dialect, the whole test oracle is independent of SQL dialect too. So the question is, how to do general semantic preserving transformation? It records our second key challenge, the complexity of SQL query semantics. So go back to these slides. We know it's very difficult to understand the semantics of a whole query if it's very complex. And now we need to do semantic preserving transformation. How to do that? The question becomes, how can we preserve the query semantic that we don't know? Is it really possible? Our answer is yes, and we can do it by fine-grained analysis. So still this query, we focus on this select, and we try to analyze the final grains of this query. So the first question is, what's the final grains of a query? Our answer is expression. If we look at this query from the aspect of expression, we will find that these queries are really simple because the expression inside are just column reference and constant in this query. And simple means it's easy to analyze. So we come up with an idea. We can transform expression instead of a whole query. It's based on the fact that if the semantic of each expression in a query is preserved, the semantics of the whole query is also preserved. So then, go back to this slide. Our solution is equivalent expression transformation. To do this transformation, we need to first figure out the expression inside the query, and then we transform this expression. So let's see how to transform the expression. We know in SQL, Boolean value could only be either true, false, or null. So we know this equation must be whole because P can only be true, false, or null. So these three one of them is true, and true or everything is true. Similarly, we can come up with this equation. We know P, not P, P is not null, one of them must be false, and false and everything is false. Second, we need to use the case expression. Case expression is defined in the SQL standard and generally supported by various database systems. So its logic is very similar to the if-else logics in the traditional programming language. So it's easy to come up with this equation. This case expression has a branch condition whose is always be true. So this case expression always refers to expr1. Similarly, we can come up with this equation. And this case expression has a false branch condition. So this is all we need to know before we do transformation. Now let's do it. Given an arbitrary expression, And we can first transform it using the case expression, using a true branch condition. Then we extend the true using the equation we already discussed. So in this way, we can transform the expression into another case expression where P and the ran expression are randomly generated. They will not affect the semantics of the case expression. Similarly, we can do it for the another kinds of transformation using case expression with false branch condition. Then we can do this and get another kinds of transformation. So talk is so abstract. Let's practice a bit. Given this query, we focus on this select, and further, we focus on these two expressions. We first transform it to two case expression with a false branch condition. Then we transform the false into this two, and we know that these two queries should produce exactly same result. But it turned out that they produce different results. One of the query output 1 row, but another query output 0 rows. So we know we trigger a bug. And actually, it's a very, very ancient bug in Postgres. It has existed for over 20 years. So using this way, we test 5 very popular database systems: MySQL, Postgres, SQLite, ClickHouse, and TiDB. In total, we find 66 bugs, and 35 of them can cause incorrect results. And we get very positive feedback from the developers of this database system. ClickHouse guys say this tool has proven its value and want to integrate our tool into their CI and use it continuously. Postgres guys say they have thought about the self-join test for 1 year and they're really interested in reading our paper. So we analyzed the bug we found and the corresponding bug triggering query. And we found that our bug triggering query involves various kinds of SQL features. For example, subquery, join, Windows function, group, or DML. And it demonstrates that our approach can effectively validate the correctness of these diverse SQL features. And we also found that most of the bugs are related to subquery and join because these two features can involve complex semantics, and it is very difficult for developers to implement these correctly, so they tend to be error-prone. We also analyzed the bug latency. So we found that among the 35 bugs that can cause incorrect result, 24 of them exist for over 1 year, and 13 of them exist for 4 years, and the longest one is the 20 years, and for each database system, at least one bug exists for over 3 years. So it demonstrates that our approach can find many long latency bugs. Okay, and that's the end of my presentation. Thank you very much. And our Pro tool is open source, and you can scan the QR code to get it, and feel free to play around it to find bugs in any database system. Thank you very much.